Okay, so this is Computer Networks, Chapter 2, Part 1 of 4. We are going to start off by taking a look at application layer and how it interfaces into the rest of the networking stack. So the Kuros in Ross textbook is called the top-down approach because it starts kind of at the highest level application layers and then works its way down to the physical layer. There are good reasons to do that, mostly because you've probably grown up using the internet and you're familiar with that top layer. You've used different applications. And so that kind of helps us understand where we are, and it's a good place as any to get started. So if you remember, the application layers are really just the top 3 layers of the OSI 7-layer model, or the top 1 layer of the 5-layer model. And so at times we're going to want to have that specificity of the OSI model, and at other times we can just lump it all together as one and kind of ignore what's happening there. For example, from the network's perspective, we don't really care whether you're displaying your email in MS Outlook or you're displaying it on your phone. What we're really trying to do is just get that message to your device. However, if we're trying to design some kind of email system for a large multinational company, we'd probably want to pay much more careful attention to the network footprint of all of those systems and how they interact with one another. And so then we would want to see that split between the different layers. In addition to lumping application layers together, one of the most important concepts is the idea of encapsulation. Sending emails or watching movies or surfing the web are all very different. And they all have different network requirements. But what we're going to find is that the application, whatever it is, can only communicate to the transport layer. And it can only present data to that transport layer. The transport layer then is completely agnostic to whatever data it's sending or receiving. The authors of the transport layer software can make absolutely no assumptions about the data that you're exchanging. And this is, by design, a very good thing. Just for a moment, imagine that the opposite thing were true. Imagine that if every time we wanted to make a new internet-based application and deploy it, that we would need to modify the transport layer underneath of it. We would need to go back and upgrade every operating system, every switch, every router, every device on the entire internet in order to handle our new app. I mean, it's impossible to imagine. I mean, that's just kind of silliness. And if we were to be inside that world, the advantage of that, though, is that we could design a new transport layer specifically to handle every new application. So, for example, if I wanted to design a better Netflix, for example, we could embed into the transport layer special instructions that would allow Netflix to reserve bandwidth for your streaming session. And so maybe you have a 100 megabit cable connection. You could actually, in your transport layer, tell the cable company to reserve 10 megabits for your 4K Netflix session or something like that. And then when you're done, you could advertise that you're all finished watching and you want all your data back for surfing the web. But we don't live in that world. And so because we don't live in that world, our transport layer is just going to move data independently of the application that's creating it. And as a result, it's really important for software engineers to understand the impacts of their design choices when building a new application. In fact, it is in this interface between the application and transport layers that the software and network engineers need to work hand in hand to deploy applications that can scale up to handle global demands. Some choices made here can be really simple. For instance, we'll pick one of the well-known transport mechanisms. But then other choices may seem less obvious. For example, maybe the application just sends huge gobs of data all at once, or maybe it breaks it up into little tiny pieces so that the transport layer has an easier job, or maybe they do it too small and we send too many messages. We spend more time transmitting network packets than we actually do data. All of those things are possible, and I've seen all of those things happen in even commercial level applications. Finally, because the application layer is typically opaque to the transport layer and lower, network core devices typically ignore the application data. So typically routers and switches don't give different priority to web traffic versus email messages versus that Netflix stream. They both get routed equally. However, there are some devices that do pay attention to the application layer. For example, a relatively new class of device called traffic shapers can actually use the information at the application layer to prioritize some types of traffic at the expense of others. Network intrusion detection systems, or IDS, can use application data to detect if somebody is trying to compromise a network and then shut down that attempt at the network edge rather than let it push its way through the network itself. So that interface at the application layer is really, really important. And so while we try to ignore the application itself, we do need to pay attention to how the application layer will communicate to the transport layer and then down into the deeper levels of the network. So this gives us the 5 key principles for understanding how the application and the transport layer interact with each other. And we'll kind of explore each of these in more grueling detail. At the very beginning, the network applications are a mixture of both hardware and software actions. Applications need to request data to be exchanged, and eventually it has to go out to hardware. And as soon as you start talking about accessing hardware from software, this really quickly becomes a job for the operating system. The operating system is going to have to manage the network hardware and provide structures to move the raw data from the network hardware, like your network card, your wireless card, back and forth. But the OS role doesn't just stop there. One of the key jobs of the operating system is to protect information from possibly competing processes. Since there is only one network, or maybe a handful of network cards, but there are many network applications, when data arrives on the network, the operating system has to look at that data and determine which process it should be delivered to, or possibly ignore it altogether. If we let this up to individual applications, then all hopes of security are going to be thrown out of the window. So for instance, it would be very easy for one application running on your mobile phone, for instance, to steal all of your data that's being put onto the network. Instead, we want the operating system to control that access and control the streams of data that one application has access to. If the operating system will manage the network stack, then it will need to provide some kind of application programmer's interface, or an API, to enable applications to make requests to the operating system to send and receive network data on its behalf. So let's back up a second and say that the network hardware card itself, like your network card, you can point at it and that's the chip, that's where the blue wire plugs into your computer. It doesn't understand anything about TCP/IP or any kind of transport layer or email or web page, or none of that. If it's an intelligent card, it might actually understand Ethernet frames. Many cases, though, it's going to be even a little bit lower level than that. And so we're going to have something that can go from that dumb card, or maybe a slightly smart network card, up to your application layer. Something needs to be in between that. And that's what the operating system is going to do. And so what we're going to want to see is an operating system provided application programmer's interface that lets you as a programmer ask the operating system to do things on your behalf. And so we're going to have things like send data, get data, open a connection, check the status of the connection, things like that, that are going to be exposed in a C library that the operating system then understands. Through a mechanism that we call system calls. So if you've had the operating systems class, we've already talked about how a system call can be made from user space into privilege mode. There will be system calls for all of these networking tasks. But because everything is wrapped up into assembler or C language compatible libraries, these same libraries can also be very easily invoked by other languages. And so this leads to the idea that other programming languages like Java or Python can also include these libraries and make the same calls. So those languages frequently provide some helper routines to make it easier for the application developer to open up connections. But ultimately, there's nothing one language can do that cannot be done in another. So for example, I program in C, I program in Java. I don't mind network code in C language. The Java networking stuff is so easy to use. It is almost silly how easy it is to make a networked Java application. Python, I'm sure, is the same way. These high-level languages like Java and Python can kind of hide and gloss over a lot of the low-level details that you have to worry about in C language. But ultimately, they're all funneling down into the same operating system calls. Different operating systems can also choose to expose different levels of the OSI stack to the application. For example, an operating system could simply expose only the Internet Protocol's transport mechanisms to you as an application developer. Other operating systems may provide lower level entry points. One really terrible example was the Unix System 5's Transport Layer Interface, or TLI. And that enabled programmers to design their own custom network stack all the way up from Ethernet up. So using TLI, you could actually create a protocol stack that actually injected raw Ethernet, not Ethernet compatible, but protocol frames at that physical level. But it was a pain, it was a horrible interface. Getting your code to use that was just a nightmare. The Windows Network Driver Interface Specification, or NDIS, is very similar in nature, but much easier to use. And so theoretically, using NDIS in Visual Studio, if you don't like Ethernet, make your own. If you don't want to use IP, make your own. In most cases, we don't want to do that. Like if I were to try to make a replacement for the Internet Protocol, I'm either going to spend a lot of time and eventually reinvent Internet Protocol, or I'm just going to make something that can't work because none of the other routers, switches, or other network core devices understand that protocol, and they're not going to be compatible, and I won't get anywhere. So most of the time, we're going to end up using what's called the Sockets API. And in the Sockets API, we can use that to establish a connection, often with some one-time setup code, such as what's shown here. And we'll look at a bunch of code examples later, like this isn't the only example we'll see. But then we can use the simple read-write system calls, and we can use that to move data back and forth between computers, just like we would use read and write to move data between files on the disk. So language independence is fantastic. It allows and kind of promotes the ability for applications to use networking technology. And once we skip over some of the hard nonsense of setting up the connection, it's really kind of easy to be able to move data back and forth. The applications architecture is another core principle of network design and applications. There are generally two versions of this, the client-server model and the peer-to-peer model. And we're going to look at some math around this later on, but the idea and some of the differences here, we'll kind of summarize them now. The client-server model is by far the most common that you're likely to bump into today. In the standard client-server model, there's an always-on host that is always listening for incoming connections. When an ad hoc client, like your computer, connects to that server, the server will evaluate the message, perform some task on behalf of that connection, and then listen for another request. While this seems really simple, the complexity of the client-server protocol increases, or the number of concurrent clients increases, the server can quickly become overloaded, and performance is going to really suffer. And so this leads to kind of the grand challenge of client-server is how do we scale client-server up? So there's a lot of strategies that you'll see. You'll see load balancing. We'll have a bunch of servers. If one server doesn't do it, we'll add two. If two doesn't do it, we'll add four. The challenge ends up being that you can fix the server problem, but then you have more server communication, and so now you have more network messages going back and forth between servers, and that's going to put more pressure on your network. If I have more servers, I need more front-end network, and that gets us back to that last mile problem. If I have enough resources from my ISP for 2 or 3 servers, I'm not going to be able to scale that up to 100 servers. The other problem that you wind up with in client server is having to specify enough server for your high watermark. Here, for example, on campus, our high watermark time is scheduling. If you had everybody on campus all trying to schedule all at the same time, you would overwhelm a handful of servers. So, we have to do some things like send appointment times and spread scheduling out over a couple of weeks. Not only does that help the registrar's office make sure that classes remain open and we can rebalance the number of seats in different sections, but it also makes the technology work a lot better. One of the big advantages today of cloud computing is you can just dynamically pay for whatever amount of computer resources you need at the time that you need it. So I might have an application that scales really, really well, and maybe for a week I need 1,000 servers, and then I can go back to 1 or 2 servers. I can contract with Amazon, and Amazon will just throw 1,000 servers at me, and it's all fine. I've got to pay for it, of course, but it's fine. I don't have to pay forever for that capability. On the flip side is peer-to-peer networks. Peer-to-peer networks communicate amongst themselves, and that's kind of where the name comes from. There's some mechanism that peers might use to find each other, but then once they've found each other, they can communicate directly between them. So in this architecture, we don't really have a single server that everybody is trying to get to. You could imagine if I wanted to share a file with as many computers as possible, I would want to be able to have as many different devices being able to serve that data as I could. For example, in a Windows lab installation, when one computer has downloaded a patch for Windows, it broadcasts and says, hey, I have this new update. And then other computers on the network can just pull from that computer as opposed to pulling it from Microsoft servers. Apple has done the same thing with some iPhone updates. So, even these big companies now are starting to embrace peer-to-peer for certain niche applications. There are some challenges with peer-to-peer, and we'll take a look at that in some upcoming slides. But just understand that at that interface between the application and the transport layer, which is what these are all about, how a client server looks at the transport layer is very different from how a peer-to-peer environment would look. One of the other challenges that gets created by applications is that there can be a many-to-many relationship between clients and servers. And what I mean by that is that the same client machine can have multiple connections open to the same server. And somehow, some way, we need a mechanism to keep them all straight and unique. When we're talking about the internet protocols, we use a combination of 5 identifiers, or what we call a 5-tuple if you're so inclined from discrete math. This tuple includes the client address, the server address, that kind of makes sense. But then we're also going to have 2 other integers that represent the client port number and the server port number, as well as the transport type. And so, for example, a client may open a connection to a well-known server port. It's going to have some anonymous port on its own because it doesn't really matter. So, for example, maybe a machine on campus has an address of 157.160.38.35. That's a valid IP address. That would, in this case, might be the source address. It uses the local port number. That's just some number, 53,234, probably not used by anything else on that computer. And it's going to try to open a connection to a server, say 157.160.28.36. That server might use a port number of 80. That corresponds to a well-known number for the World Wide Web. And if they're using the TCP transport, we get those 5 values. We get the source address, the source port, the destination address, and the destination port, as well as the fact that it's TCP. And that is a globally unique combination of information for the entirety of that connection. In fact, there can be no other in the entire universe. There can be no other IP connection that shares those 5 values. And so having just 5 numbers to be able to uniquely identify a connection on the internet is really very valuable. Even if the same computer were to open up another connection to the same web server, the destination port, port 80, would be the same, but it would have to be a different local port because the other 53, 234, or whatever the source port was, that was already in use. And so there would have to be a different port used for a different connection, and that would still make it unique. We'll come back and look at some of these things later on as well. But it is how we can have many clients connecting to the same server, or you could be using different web servers at the same time. Like if you're one of those people who have 1,000 browser tabs open, you can do that, and your computer can keep them all straight. Another principle is the different kinds of transport types. There are 5 general transport types that applications can use, and they're based on reliability, throughput, latency, security, and mobility. Reliability means that a sent message will arrive at the destination, or that the sender will be notified of the failure. The protocol may need to resend data to correct for errors or for corrupted data, but the transport protocol will do that without any intervention from the application. So in a reliable data transfer, your application says, hey, operating system, send this block of data, and somehow you'll either be told, yep, that block of data was received at the remote end, and now the remote side is ready for more, or nope, it didn't get there. So that's really a nice goal to have. Throughput is a guaranteed, say that again. Throughput guarantees are desirable for applications that must move large amounts of data quickly. Typically, the application has a mechanism to request some minimum amount of data, for instance, bits per second, that it can reserve for transmission. For example, a streaming service may want to sustain some minimum number of bits per second to keep the stream alive and not drop any frames. So when you have a throughput, you might be willing to sacrifice some reliability to get that higher speed. Timing or latency guarantees enable an application to send data with some upper bound on the delay of transmission. For example, a digital telephone network may require a maximum of 100 milliseconds of latency to avoid detectable pauses in a conversation. Anything more than that, and your ear will hear it. And so timing guarantees can be really valuable for certain applications. Security has emerged as one of the most important transport types, obviously in recent years. The idea is that the application can offload the encryption onto the network itself, enabling more secure and strong implementations of the cryptographic algorithms. And we could possibly offload those rather expensive calculations onto dedicated encryption hardware that's possibly even built into intelligent network devices. A good example of this might be VPN connections or appliances that we can plug in to do virtual private networks. The encryption for the VPN itself is going to be done on application-specific integrated circuits, or ASICs, and it can be done much more efficiently than in software. Finally, mobility is becoming an increasing challenge. And to kind of make you understand or help you understand why that is, as mobile users move around, the best connection between a mobile device and a server can change, and it can change many times. When you're plugged in to a desktop, maybe the mobile device is going to favor a tethered connection. As you walk around a building, the high-speed Wi-Fi may be faster and more reliable than your cellular data, but it may not be, like if you're at a coffee shop, it may not be Wi-Fi that you trust. So maybe some connections you would want to know, I don't trust Xfinity Wi-Fi because it's kind of open and public, not to diss Comcast, but I do trust Ship's Wi-Fi, or maybe it's vice versa, whatever the rules are. At the edge of a building, there may be two equally poor choices. So as you get to the edge of the building, maybe the Wi-Fi zone isn't as strong and the cellular connection isn't as strong, and you may end up losing connection entirely. However, as you leave the building, maybe you're back to a strong cellular connection. But cellular connections are often metered, and you pay per bit. And a connection that's established on that one network, maybe the ship network, isn't going to be able to migrate to your cell phone network. Remember that 5-tuple that identifies a connection? Imagine if you were in the middle of watching a movie on Netflix, and you go from being on campus and your source IP address and port number are a campus address, and you transition over to the mobile address, your mobile phone is through your cellular provider is going to be a different source and port number. If we change any of those 5 tuples, the connections are going to break. Later on, when we look at different content distribution networks, it may even be that we go from a content distribution server that's on your one ISP that's a different one on a different ISP. So mobile just really wreaks havoc. And unfortunately, in many cases, we're going to need the application to fix that, because there's just not going to be a lot of support for that from the existing transport types. If you were to make a better mobile transport type, I think there's a lot of developers that would be very grateful for you. Unfortunately, when we look at what's provided by the internet transport mechanisms are quite limited. And they're limited by the very nature of the packet switching and routing systems that are used to make the internet work at all. So unfortunately, we're really limited to just saying we want reliability or a potentially higher throughput mode, but we're not going to be guaranteed anything. Because we can't control the path that a packet will take through the different internet exchanges, we can't set upper bounds on latency or minimum bounds on throughput. I could ask, even if there were a mechanism for me to ask my service provider to give me a 10 megabit connection for Netflix, there's no reason to expect that some internet exchange is going to honor that. I mean, that would be really kind of not in the spirit of how the internet works. There are no guarantees that a packet will even arrive. And if it does arrive, there's no guarantee that it wasn't broken up into small chunks and that those chunks have arrived in order, or that there's going to be an upper bound on the length of time that it takes for all of those chunks to arrive. Consequently, application developers need to keep this in mind. While the app devs can shirk some of the responsibility onto the network transport layer, they can't get all of these interesting guarantees. So for example, if I want to have a low latency delivery, I'm probably going to want to go ahead and use one transport mechanism over another. If I choose rightly, then my application is going to need to manage sending data and manage how much data it puts out there itself. So as an application developer, I'm going to need to work with the network engineers to kind of make that happen. On the other hand, if I'm just going to use the transport layer as a reliable transfer, I'm going to get whatever I get. And so maybe that's going to work, or maybe that's not going to work. And so as an application developer, I need to know what I'm losing by using reliability baked in at the transport layer. And these become not easy decisions. There's always going to be some kind of a trade-off. I can get reliability pretty easily, but at the cost of some performance. I might be able to get performance at the cost of really, really complicated code. And so it's really hard to predict how it's going to look. There are two principal transport types that are provided by the Internet Protocol. The first, Transmission Control Protocol, or TCP, which is what we're looking at right now. And on the next slide, we'll talk about the User Datagram Protocol. And we'll talk more about these in the next chapter as well. But as an introduction, TCP is a connection-oriented protocol. Each connection has a state on the client and the server. And the TCP transport layer sends messages between the client and the server to maintain and update that state. After a connection has been established, and there is some protocol for getting the connection established, then the endpoints can simply exchange data using reads and writes until one or the other side closes the connection. So from the application's perspective, we read data or we write data, and it magically gets there. The connection that's established is full duplex, meaning that both endpoints can send and receive data. We can't do it at exactly the same time, but pretty darn close. So because of the way Ethernet works, if an Ethernet segment is shared media, then you only have the ability to be sending or receiving at one time. Some of the twisted pair stuff can actually have a transmit and a receive pair, and then it can really truly be full duplex. But everything in between also has to support that. It's more common today than it was a few years ago. The TCP is absolutely a reliable transport. Again, when the sender sends data, the data comes out of the other end whole, in order, and free of errors. If not, the sender is going to be notified that the transmission was they tried to retry it. The transport layer issued retry commands, but it still failed. Eventually the state machines give up, and then this connection gets closed, and then you get an error message. The important thing is you know that the sender got the message or not. Beneath this facade, though, the data may actually arrive with fragments and errors and out of order, and it's going to have to be managed. Of course, that also means that there's going to be messages that are exchanged back and forth between the TCP transport layers that are not data messages. We call those out-of-band messages, messages that are not the kind of main data that we're going to send and receive. That also, therefore, means that we're going to be sending more data, more messages, than the actual data messages. So to send 1K of data, I might send 10 or 12 messages or more if I have to do a bunch of retransmits. So there's going to be overhead for this reliability. And that's one reason why we'll see applications sometimes look for the UDP for non-reliable but higher bandwidth. The exchange of messages also tends to create natural congestion control. The TCP stack will only send so many chunks of data at a time before the remote endpoint can acknowledge. And so if I send a whole slew of data, I'm going to have to eventually stop and wait to make sure that the remote got the data. And then once the remote sends the acknowledgement message, then I know I can send more data. If for some reason that acknowledgement doesn't come in, then we'll send the data again. And in the meantime, the remotes be like, hey man, I already got that stuff. And so they'll negotiate back and forth. And that kind of slows things down, and it keeps one side or the other from saturating the links in between. So on the next slide, we'll take a look at an example of two TCP endpoints communicating.
Okay, I wanted to go through an example of using Cisco Packet Tracer to simulate an application running on a network and use it to see some of the messages that get exchanged. So to do that, I'm going to go ahead and open up one of the samples that comes with Packet Tracer. And so it's opened up this whole list of examples, and I'm going to open up the HTML, and I'm going to open up HTML JavaScript style sheet. And what they've done is they've created a small network. It has a PC, it has a server, and it has a connection in between the two of them. The display here is showing that the link status between the two is good and that they can communicate with one another. There's some instructions here that are telling me what to do. So for instance, if I were to click on the PC, we see the kind of physical configuration of the PC. I'm really interested in just going to the desktop. If I kind of resize my window here, I see that there is a web browser, and if I go to the web browser, now I can go ahead and open up the URL that they give here. And basically what's happened is it's contacted the server. Let me go ahead and open that up. Do this. So this is the server, and it has a bunch of other physical configuration. It also has some services, and in particular, it has a web server, the HTTP server, running on it. So basically, the demo that I was able to do here just kind of shows being able to open up a web page. Now that's interesting from running a simulation program. But I'm actually interested in being able to see the actual packets that are being exchanged. And so instead of running this in real time, I'm going to go here to simulation, and the slider down here lets me pick how fast or how slow the simulation runs. And right now it's effectively off. I can also click on this reset simulation and kind of start everything here at 0. And what we can now do is go back to our web browser. And I'll just go ahead and open up that request again. Now this time, instead of immediately coming back with the values, what we see is a message has been prepared. And if I were to click on that message, what we see is a TCP frame that's been created, and it's going to be put onto the network. Now it hasn't actually been put on yet. It's stalled because the simulation has no time, like it's not running. But I can see that a request has been made. And so basically this is the PC as part of that handshake, that TCP transport negotiation of, hey, can I open this connection? Yes, you can. Here's some data. I acknowledge I got your data. Here's the response. I mean, all that stuff that gets sent back and forth to make a reliable data service. This is the first step. And so we're going to try to open up a connection to that destination port 80, which is the well-known service for a web server. And we're going to give it the source port of 1026, which apparently is just one of the first unused ports on this server. We also see that it's a TCP layer, and so that's part of that 5-tuple that we talked about in the lecture about making this connection unique. Of course, the other two pieces are the addresses for the machines. The source IP address is 1.1.1.2, and the destination address is 1.1.1.1. Both kind of fictional addresses for this kind of Cisco packet tracer environment. So this is kind of typical for a TCP service. We look, there were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 individual operations here to just pull one TCP frame, one HTTP request from a server. Of which a bunch of this stuff was just the overhead of TCP requesting and acknowledging and kind of establishing the connection. So Packet Tracer makes it really easy to visualize how things are moving back and forth. I think it's a really nice opportunity to really get kind of down into the nitty-gritty of some of this stuff. As we go through the semester, we'll spend some more time with Packet Tracer. So anyway, this is the first example using TCP.
Our other transport type is the user datagram protocol, or UDP. UDP is stateless, so neither side, neither of the endpoints is going to maintain state. The UDP stack doesn't keep track of anything that happened before, unlike TCP. The UDP stack doesn't guarantee reliability. The application needs to do this. So for example, if I'm going to send data to you and I want to know that you got it, then when we develop our application, then you need to periodically send me UDP messages that say, yeah, I got your data. And so maybe I'll throw a whole bunch of data at you and I'll expect just to count. How many packets did you get from me? You say I sent 100, you say I sent 50, then I know that you've lost somewhere in between. Someone's lost a whole lot of data. that could be as simple as that, or it could be even more complicated. But either way, it's the application that's going to do this. Um, no congestion control, and that's kind of by design, right? If we're going to have a higher bandwidth protocol, we don't want to have some kind of artificial congestion control imposed. We want to move data as fast as we can. But understand that as a consequence of having no congestion control, remote devices between me and you are free to drop UDP packets like hot potatoes. So there's no guarantee that the path that my data takes, that's a switch along the way, is not going to be like, hey, this guy's using 9/10 of my bandwidth. We're going to start dropping excessive packets. So in many cases, the application needs to set its own speed limits and apply brakes if it detects that things are just being dropped too frequently. Because sometimes the application is more information than the network stack does. And I think, I was trying to think of good examples, and the one that came to my mind is one of the best examples of UDP was the Andrew file server. The Andrew file server, or AFS, became popular in the late 1980s and was used throughout the 1990s. AFS was able to scale up to tens of thousands of concurrent users at a time. Now, when you think about computers in the 1990s, we're talking about computers that maybe were 33 megahertz, whereas today computers are several hundred times faster than that. And so to be able to handle and scale up to that huge number of concurrent users was really remarkable. In fact, AFS could share files across the internet. It was kind of built into the security of AFS that it was a file server that was secure to be wide open. And so we could actually share files with other universities. And it was pretty common to do that. In fact, before the World Wide Web, AFS was how many scientists shared data sets. So as a scientist, I could post a data set to my AFS directory and then just give you the AFS address to find my file. AFS relied on UDP messages. So as a result, the AFS servers didn't need to keep state for the connections that may never be used again. And that's really the secret to their success, because the servers don't take up state. They don't have to keep track of all those 10,000 concurrent connections. There's a lot less memory overhead that way. I don't have to maintain tables of connected clients. I don't have to maintain lists of users and files that are open. On the flip side, the UDP messages had to include encryption and security tokens to enable the AFS server to validate every client request and ensure that the data could not leak to someone who shouldn't have that data. So on the one hand, we've taken the complications of maintaining TCP state away from the operating system, and we've replaced it with these UDP messages that have, kind of the information that would normally be part of state encrypted into the messages itself and the tokens that allowed these things to communicate back and forth. There's a lot of really interesting design ideas that AFS provided. The only reason, like I said, I bring it up is because we don't typically see it anymore. It's kind of gone the way of the dodo. It was really cool for the time. It did all kinds of neat things, but it just isn't used anymore. And it wasn't really a bad design. It's just, why we don't need to use it when we have things like Google Drive or OneDrive or the web itself. So the technology has moved on and kind of made it more redundant. So on the next slide, we'll take a look at an example of UDP and how UDP messages are exchanged between endpoints.
Okay, so just as we did a packet tracer for TCP/IP, I want to do a packet tracer demo for UDP. Well, I'm going to do basically the same thing. We're going to go ahead and open samples. I'm going to navigate this time to TCP/IP, which is kind of ironic that we're going to TCP/IP for a UDP example, but I'll give Cisco a break on this one. I'm going to go ahead and pull up the TFTP packet tracer. TFTP is a server, client server thing that allows you to transfer files without any kind of um, username and password. It stands for Trusted File Transfer Protocol. And so what we're going to do now is I'm going to go to simulation. Our speed here is set for 0. And I'm going to just kind of follow the packet tracer instructions. And basically the server is running a TFTP server and the router is running a TFTP client. So if I were to go to the command line interface for the router, um, basically this is the interface that you'd use for manually configuring Cisco gear, their iOS operating system. Let's go ahead and give it a little CPU time. Now you'll see messages kind of going back and forth, and this is just the devices negotiating with each other. But if I type in enter, we can actually type in a command called enable, and that will enable me to be able to run privileged commands. Normally there'd be some kind of user ID and password. This is like becoming root to a Unix system. If I just type in the command here now, I can type in copy run tftp, and it's going to ask me what the address of the host of the server is. And so the server, they even tell you right here, is 10.1.1.2. And when I go ahead and hit enter, we'll actually be able to see these messages start to be exchanged. Now, before the TFTP can start, it needs to know the MAC address of the machine that it's running on. Let's give it a little bit extra CPU speed here. And so it's going to use this thing called Address Resolution Protocol, or ARP. We'll talk about that on a different time. Might need to give it even a little bit more speed. So it's still trying to figure out what Ethernet device has the IP address for the server. And it looks like it just found that. So we see now that the TFTP request was made, it was received, the server responded, and now the router is making another request, and it responded. And I think it should, yeah, and basically we're done now. Now I want you to compare, if we ignore, let's go ahead and stop the time again. If we were to ignore the ARP messages, because they're kind of outside of, once you know the remote machine, you don't need to ARP, so it's kind of not related to the TFTP. And these CDPs are like the Cisco Discovery Protocol, I think is what it stands for. They're just broadcasting to say, hey, I'm alive. We can ignore those. So really, ultimately, what we're seeing is just a handful of packets. Let's take a look at one of these things. Here we see that this is a UDP message. It has a similar port number and destination port number and things like that. We see the same layering, so it goes from the TFTP layer down to UDP, down into IP, down to Ethernet 2, over an Ethernet cable. The packet tracer doesn't really dissect the packet any further, so it knows that it's TCP data, TFTP data, but that's about all it knows. But we can still look at this and say, well, we moved a whole pile of data here, and there was none of that overhead from the TCP. There's no opening the port and checking the port. There was no acknowledgement that the data was sent or received. It was literally, I make a request. Let's see if we can find that first request. So this is the router to the TFTP server. Let's see if we can see what file it's asking for. It doesn't show that file. If we were using other tools, like I know Wireshark would actually dissect the message here. We could actually use it to read what file was even being requested and all of the other details. But UDP, it's literally just going to be the application layer is driving everything. And so that does make a pretty big change from the TCP layer. So hopefully you can see that without too many of the other details. Sometimes it's hard to simplify away some of the behaviors here. But as we kind of go through, some of this stuff will make more sense. I would encourage you guys, you can really kind of do some neat things now with Packet Tracer. Um, and we'll do a bunch of examples in class. We'll see what happens, for instance, we can do a peer-to-peer thing and throw a bunch of hosts together and watch how the network links change. But this just gets you started.
Thanks for watching. We'll be back for part 2, looking at application protocols.